Hi, in my previous video I talked about fractals, what they are, we will use them, and how to create one using C++. You can watch that video if you haven't yet, but I'll recap it in 15 seconds. Today, I'll focus on the graphical implementation of zooming into the so-called Mandelbrot Set, which you can see on the screen. First, a small reminder, a fractal is a geometric object that you can zoom in infinitely many times, and the Mandelbrot Set is an example of a fractal. Let's have a look at the code from the last video. I made some modifications here. Mandelbrot Set is a class that has one important method called renderFractal. Basically, this method generates the image of the fractal and saves the color of each pixel into the vector image. It has 4 fields which specify a rectangle on the plane to generate. By default, this rectangle includes the whole Mandelbrot Set. When you select a specific region of the fractal, these numbers are changed to show a more specific part of the plane, or less specific if you want to zoom out or reset the zoom. I added 2 methods. The first one is updateRegime, which simply updates the region of the plane to show. The second one, setDefaultRegime, sets the region to the default value. It's the state where you can see the whole fractal. Also, I changed the function renderFractal a little bit. In the last video, I mentioned that you can apply multi-threading. This is what I did. Now this function creates many threads, and each thread renders only part of the fractal using the function renderFractalPart. That's all you need to know about this file. Let's have a look at the main.cpp file. Before going any further, I gotta tell you about the SFML library which I use for graphics. If you compile or run the code on Linux, you can download this library with the following command. If you're a macOS user, use this command. If your operating system is Windows, uninstall it and install Linux. Jokes aside, follow the instructions on their official website. Let's return to the code. Here I specify some parameters, like the size of the window and max error, which is a parameter needed to create a Mandelbrot set. If you increase any of these numbers, you will get a better quality, but it will work slower. In the next line, I get the number of threads to apply multi-threading during rendering a fractal. Then I create an application, which is the main object that contains the whole graphics logic. So let's explore the class application. It's a bit of a large file, but when you create a graphical interface, even in Python, there will always be many lines of code. You need to create different objects like buttons or text fields and set their parameters like size, position, color, etc. It's really simple but requires lots of code, so bear with me, I'll explain everything. In this file, I named all class members with the prefix m_, which is a Microsoft coding convention. So if you see a variable like mWindow, mImage, mSelectionRectangle, etc., keep in mind that these variables are members of the class application. In the constructor, I initialize these members. When I initialize a window, I set 2 flags to add a title bar and a close button to the window. Let me explain how to display a fractal on the window. If you have no experience with graphics, it might seem a little bit tricky. Application has a member fractal, which in turn has a member image. Image contains information about each pixel, that is, the color of each pixel. To draw these pixels on the screen, I have 3 members in the application class. The SFImage class is used for loading and manipulating pixel data. However, SFImage cannot be drawn directly to the screen. The SFTexture class is used to store the image data in a format that the graphics card can efficiently draw. This is necessary because the graphics card cannot directly use SFImage for rendering, and the SFSprite class is used to draw the texture to the screen. Here's a scheme of how it all relates to each other. We draw a sprite on the window. The sprite has a texture, and the texture stores the image data. With this knowledge, let's return to the constructor. First, I create an image object and I call a method renderFractal, which basically sets the pixels of the image. Actually, it could be optimized. If you look at how I implemented this method, you will see that first, I render a fractal using the code from the last video, which saves the data to the image vector. Then I copy this vector to the m_image in the function setPixels. However, you can save the fractal directly to mImage and not use the member image of the fractal at all. Anyway, then I load this image to the texture and set the texture to the sprite. Next, I set a selection rectangle, which is a red rectangle that you can see when I'm dragging the mouse. I set its color. The last component is opacity, which I set to 0, so it doesn't have any color inside it, but I set its border to red. Then I load the font. For this I have a file Times New Roman with an extension .ttf, which I downloaded from the internet. The last step in the constructor is to create two buttons. For this I have a function createButton, which is truly boring. Here I specify the size of the button, its color, position, border, and I do the same for the text object, which is placed upon the button. I hope you're still with me. After creating an application object in the main file, which means the constructor was called and all graphical components were initialized, I call a member function run on it. Let's explore this function. It runs while the window is open. If the window is open, it waits for the event using a method pollEvent on the window object. In my case, there are several possible events. You can click a button, change color, you can start selecting a rectangle with a left click, you can drag the mouse to select it, and then you can release the left click to zoom in. Also, you can click a button, reset zooming, and finally, you can scroll the wheel to zoom in or out. Quite a few events actually. And I forgot to mention one which I handle separately in the first place. It is the event closed. This is when you click the close button. In this case, I close the window and exit the function. If it's any other mentioned event, then I handle it, draw elements on the window, and display them. Let's have a look at the handleEvent method. First, it checks whether the event is a left click, that is, event type is mouse button pressed and the button is mouse left. If so, there are three possible scenarios. First, we could click one of the two buttons. Here I check if the change color button contains a point on the window where we clicked the mouse. If so, it calls a handler for this button, and I do the same for the other button, which is a button to reset zooming. A handler for change color button is pretty simple. I change the value of the field color and update the colors of pixels by calling the method setPixels, which uses the value of color. Then I update the texture and sprite. A handler for reset zooming button is even simpler. I call the method setDefaultRegime of the fractal, which merely sets the with me draw to its default value, which is the area on the plane that includes the whole fractal. Then I re-render the fractal and update the texture and sprite. If we made a left click but didn't press any button, then we started selecting a rectangle for zooming in. In this case, I set dragging to true and fix the position of the window where we made the left click. Dragging is a flag to indicate if the user is dragging for selection. Well, we're done with handling a left click press and we have three more events to handle. Here we check if the flag dragging is set to true, which means that we have pressed the mouse before and now we're selecting a rectangle. But it also checks if our event is releasing the left button of the mouse. It means that we were selecting a rectangle, but we released the left click. So now we need to record the area that we selected and perform zooming in. I save the point on the screen where we released the mouse. Then I call handleZoomIn. First, we set dragging to false. After that, I check whether the start and end points aren't overly close. Because if it's almost the same point, then we will get a single point stretched over the whole screen and we'll end up with a dark screen. Then I call the function adjustSelectionRectangle. This function returns something, but I don't need its return value here. For this reason, I use stdignore to show that I'm aware of the fact that I'm ignoring the return value. In this function, I'm adjusting the point where we released the mouse because the image of the fractal must have a ratio of 4:3. So we calculate a new width and then adjust the height according to the value of the width. Until now, our x and y coordinates were measured in pixels, but to render a specific part of the fractal, we need to update the values of x and y on the complex plane. So here I do a simple scaling to convert pixels on the screen into points on the complex plane. Then I hide the red rectangle by setting its size to 0. Finally, I update the region of the fractal, render it, and update the texture and sprite. Well, we're done with handling zooming in. Let's go to the next event, which is selecting a rectangle. So the field dragging is set to true, but the mouse hasn't been released yet. In this case, we fix the current position of the cursor and call handleDragging, where I adjust the size of the rectangle using the same method that we used in the handleZoomIn method. and then I update the size of the rectangle. Simple as that. We have only one event to cover, which is scrolling the wheel of the mouse. Delta equals 1 when we scroll up and -1 when we scroll down. So we call the method handleZoomIn by scrolling, passing delta and the coordinates of the mouse as the arguments. Let's see what happens in this method. Here we see the same ideas as we've seen before. Zoom factor equals 0.9 when the delta is equal to 1, otherwise it equals 1.1. Then we calculate a new width and height by multiplying the old values by the zoom factor. It means that when zoom factor is less than 1, we get smaller width and height, which means that we are zooming in. Otherwise, we are zooming out. Then I calculate a new area of the plane such that the new region is centered around the mouse position. It means that the new region is adjusted to keep the mouse position fixed in the view. Finally, our standard practice. We update the region, render the fractal, and update the texture and sprite. Here's one method I didn't cover but mentioned. We call it in the run method after handling each event. The name is pretty much self-explanatory. We draw the sprite, 2 buttons, and 2 text fields. And we also draw a selection rectangle, but only if the field dragging is true. I guess that here you can do a small optimization. Since our buttons and text fields are the same all the time, you can create a separate static texture and sprite for them. That's it for the code, and instruction on how to compile and run it you can find in the README file on the GitHub repository, a link to which will be in the description. It wasn't easy, and if you have any questions, feel free to ask them. I'll be glad to answer. Be happy, stay healthy, and take care.